Hello. The last section of Chapter 2, Section 2.5, is about probability and statistics. I think the most powerful thing about Mendel's work is that he came up with these two laws, and if you take those two laws and combine them with probability and statistics, it allows you to make predictions, quantitative predictions, which is an incredibly powerful thing to do. As far as usefulness goes, one useful thing is that animal and plant breeders are concerned with the types of offspring produced from their crosses. So from an economic perspective, it's very useful to be able to predict the outcome of crosses in livestock and crops. Humans, parents are oftentimes interested in predicting the traits that their children might have. This is particularly true for individuals where certain genetic disorders might run in their families, like cystic fibrosis that we just talked about. So let's first talk about what it means. So probability of an event is the chance that the event will occur in the future. It's the number of times an event occurs divided by the total number of possible events. A common way to think about this is think about how you flip a coin. The probability of heads would be one heads, which is the event that we care about, divided by the total possible events, which would be one heads plus one tails. So that equals 1/2, which equals 0.5 or 50%. The accuracy of a probability prediction, though, it depends on the size of the sample. There's usually a deviation between the observed data, so that's the data that we collect, let's say from an experiment, and the expected outcome, which is what we would predict based on our understanding of the inheritance pattern. And so this deviation is due to what's called random sampling error. Sometimes people call it random chance. The random sampling error tends to be large if the sample size is small, and vice versa. It tends to be small when the sample size is large. For example, if we flipped a coin 10 times, we wouldn't be too surprised if we got 7 heads and 3 tails. So 70% heads, 30% tails. That's a pretty big random sampling error. It's 20%. It's 20% deviation from 50%. However, if we flip the coin 1,000 times, the percentage of head would be fairly close to the predicted 50% value. So the relative percentage of this random sampling error tends to be really small if the sample size is really large. Okay, and we're going to come back to this when we get to talking about hypothesis testing at the end of this section. What we're going to focus on first is using probability calculations in genetic problems to predict the outcome of crosses. And we're going to think about two different mathematical operations. One of them is the product rule, which we'll talk about first, and then the other one is the binomial expansion equation. Product rule. Big and red, it's got to be important when we see that big red bold font. The probability that two or more independent events will occur is equal to the product of their respective probabilities. Independent events are those in which the occurrence of one event doesn't affect the probability of another. So as an example, let's consider the disease congenital analgesia. It's a recessive trait in people. Affected individuals can distinguish between sensations, but they don't feel things as being painful. You might think, well, that would be an advantage, but actually it's a disadvantage because, especially in small children, it's very easy to hurt yourself and not realize it. And so the things that people who don't have congenital analgesia would learn to avoid, people with the disease can actually hurt themselves and sometimes bleed to death. It can be quite serious. There's two alleles. There's capital P, which is the non-disease causing allele. We're not going to call that the normal allele. Some people might, but we're going to call it the non-disease causing allele. And then little p is the recessive allele that causes congenital analgesia. So here's our question. Two heterozygotes plan to start a family. What's the probability that the couple's first 3 children will all have congenital analgesia? We can apply the product rule. First thing we need to do is to calculate the individual probabilities. and this can be obtained via Punnett square. I'm not showing the Punnett square here. The cross would be big P little p cross big P little p. And if we did draw a Punnett square, the ratio from that Punnett square would be 1 homozygous big P, 2 heterozygotes, and 1 little p. So 1/4 of the offspring would be little p. And so the probability of having congenital analgesia would be 1/4. Step 2 is we multiply the individual probabilities. Now remember, our question is the first offspring has it, the second offspring has it, the third offspring has it. So we multiply 1/4 first offspring times 1/4 second offspring times 1/4 third offspring, which equals 1/64. And then 1/64 can be converted to 0.016. Or another way of expressing that is that 1.6% of the time, the first 3 offspring of a heterozygous couple will all have congenital analgesia. And as you might have expected, it's a fairly low number. So that's the product rule. These are independent events. Another type of calculation uses a binomial expansion equation. So this represents all of the possibilities for a given set of unordered events. The reason why the events are not independent is because we're thinking about a group. So let's say we were asking the probability of a family of 5, 2 blue-eyed children and 3 brown-eyed children. Okay, if the first 2 children were blue-eyed and the next 2 children were brown-eyed, then the 5th child would have to be brown-eyed to satisfy that type of family. So if it was 2 blue and 3 brown, all 5 events are not independent of each other. Okay, if we already have determined 4 out of the 5 events, the 5th one is fixed. Okay, so it's not independent. So here's the equation. You can look at what the symbols mean. We're going to be calculating the probability. N is all of the total number in the group, like 5 in a family. X is the number of events of a given category, let's say blue eyes. And then P would be the probability of blue eyes, and Q would be the probability of the other category, which would be brown eyes in this case. So the binomial expansion equation applies to situations where there's 2 possibilities, like let's say only brown and blue eyes are the only possibilities. In your textbook, it talks about the multinomial expansion equation. So this equation can be expanded to include more than 2 categories. So you might want to take a look at that. In the case of 2 possibilities, P is the probability of one possibility, one phenotype, and Q is the probability of the other phenotype. If those are the only 2 possible phenotypes, then those have to add up to 1. The symbol exclamation point denotes a factorial. And just to remind you, n factorial is the product of all integers from n down to 1. If we're talking about 4 factorial, it would be 4 times 3 times 2 times 1, which equals 24. An exception is 0 factorial, which happens to equal 1, which is, you just have to remember that. So here's our question. 2 heterozygous brown-eyed individuals have 5 children. Okay. What's the probability that 2 of the couple's 5 children will have blue eyes? So first we need to calculate the individual probabilities. Again, I'm not showing the Punnett square, but the cross is big B, little b, big B, little b. You have to be, the little b, the blue allele is recessive, so you have to be little b, little b. So 1/4 of the offspring would have blue eyes, 3/4 would have brown eyes. We determine the number of events, n's the total number of children. 2 is x, the number of blue-eyed children. We could flip this around. We could have x as the number of brown-eyed children. Okay, but if x is the number of blue-eyed children, then p equals 0.25 or equals 1/4. Okay. If x was the number of brown-eyed children, then p would be 3/4. So the p has to correlate with what x means. Okay. So here's our equation. You can pause and and look through the numbers if you like. So here's 1/4 is P, the probability of blue eyes, 2 children with that. 3/4, the probability of brown eyes, and that's 5 minus 2. And so we end up with a value of 0.26 or 26% of the time. So that's useful because sometimes in genetics we're interested in predicting the outcome of a family, a group. Okay, the last thing we're going to talk about in section 2.5 is the chi-square test. So it's a statistical method to determine goodness of fit. So it's based, oops, went too fast there. Goodness of fit refers to how close the observed data are to those predicted from a hypothesis. So a hypothesis will give you expected data, the observed data you gather from an experiment, and we're comparing those two things. Remember, the chi-square does not prove that a hypothesis is correct. It just evaluates whether or not the data and the hypothesis have a good fit. And then you decide, based on what probability value you get, whether or not you want to accept or reject your hypothesis. Here's a general formula. So chi-square, don't take the square root of chi-square. Students want to do that. Don't do it. Don't do it. That's just a symbol because it's meant to represent deviations from between observed and expected values. So you sum this term multiple times. And as we'll see in a few minutes, if you've got 4 phenotype categories, you'd have 4 of these terms that you would add together. So O is the observed data in each category, E is the expected data based on a hypothesis, and the sigma symbol represents the sum of the calculations for each category. So let's go through an example. Let's say there's a gene affecting wing shape. Actually, there is. E plus gives you normal wing. I'm sorry, C plus gives you normal wing, and C equals curved wing. There's a gene affecting body color. E plus gives you normal body color, and little e is ebony. The wild type alleles is designated with a plus sign in fruit flies, and the recessive mutant alleles are designated with lowercase letters here, as we've been doing in other situations. So we're going to cross 2 true reading flies. Here's our cross. And the flies of the F1 are then allowed to mate with each other to produce an F2. So the F1 generation all have straight wings and gray bodies, and the F2 have this. So if you remember back in section 2.3, in this type of an experiment where we're crossing 2 double homozygotes, we would expect a 9:3 to 3:1 ratio. Okay. So here's the observed data. Now to apply the chi-square test, the first step is we need to propose a hypothesis. So here we're going to propose that the 2 traits are independently assorting. And so if they are, then the expected probability is 9:3 to 3:1 ratio. So 9/16 of the offspring should be have straight wings, gray body. There were a total of 352, so we would have expected 198. We would have expected 66 in this category, 66 in this category, and 22 in this category. So what we're going to do is we're going to add these together, these different things. So 193 was the observed, 198 is the expected, divided by the expected, 69 is the observed, 66 is the expected, and so forth. So if we add all these things together, okay, we come up with a chi-square value of 1.06. Now what do we do with this value? So in order to interpret that value, we're going to have to convert it to a probability, and we'll talk about how that works in a minute. But before we do that, we have to determine the degrees of freedom. So what we're wanting to get is the p-value from a chi-square table, and these probability values will allow us to determine whether or not the likelihood that the observed deviations are due to random chance alone. What's the likelihood? So a low chi-square value indicates a high probability that observed deviation could be due to random chance alone. Whereas a high square value, when the observed and expected deviate a lot, then there's a low probability that that would be due to random chance alone. And so then you get suspicious, well, maybe the high chi-square value is because the hypothesis is wrong. Okay, so when you get a high square value, you tend to reject your hypothesis. And there's different conventions. If the probability ends up being less than 5%, we may reject the hypothesis. Or some people will use a somewhat more rigorous 1%. Before we get into the use of the chi-square table, though, we need to determine the degrees of freedom. It's the measure of the number of categories that are independent of each other. And degrees of freedom equals n minus 1, where n is the total number of categories. In our experiment, there are 4 phenotype categories. So degrees of freedom, 4 minus 1 equals 3. And remember that our chi-square value was 1.06. So we're going to look at our table. Well, you kind of have to remember these numbers here. So the degrees of freedom equals 3. The chi-square value equals 1.06. And so in a minute, I'm going to show you the next slide in a minute. But in the chi-square table, that's going to give us a probability that's close to 0.8. So let's look at the table here. So here's our degrees of freedom. Our chi-square value was 1.06, so it was close to this number. Okay. So chi-square values that are equal to or less than 1.005 are likely to occur about 80% of the time. The p-value equals 0.08. So if we go back to our previous slide, a value of 0.08 means that there's a pretty high probability that that chi-square value could be explained by random chance. So because of that, we're kind of feeling good about things, because 80% of the time we would have got that random sampling error, that small of 1. So the observed and expected values are pretty close together, and so we would accept our hypothesis. So as it says in the last sentence here, therefore it's quite probable, 80% probable, that the deviations between the observed and expected values can be explained by random sampling error. So we have no basis for rejecting our hypothesis. As we've already said, it doesn't prove your hypothesis. You just have no basis for rejecting it. Okay, so anyway, that's all I want to say. We're going to return to the chi-square value when we get to Chapter 6. It'll be a nice tool that we can use if we want to try to distinguish whether or not 2 genes are located on the same chromosome. And so our chi-square test can be used in that situation. Okay, well, that ends Chapter 2. In Chapter 3, what we're going to try to do is to relate Mendel's work, inheritance patterns, with what's happening with chromosomes at the cellular level. And we'll go through processes that you've learned about probably in a general biology course, which are mitosis and meiosis, that helps us to understand how genes are transmitted from parent to offspring at the cellular level.